Today I'm working with my contestant Shy here, and we're investigating randomness and probability. We're going to do that using the famous Monty Hall problem. Have you heard of Monty Hall? Mm-hmm. Is he alive or dead?
I think he's dead.
I think he might be dead. He was the host of a game show called Let's Make a Deal, in which he would make all kinds of crazy deals, and this is one of them. He would show a contestant, here's an example, 3 doors, and then the contestant would randomly choose one. Just choose that one. Right. And then he would say, okay, before I show you that, I'm going to show you that this one here is empty because he's got 1 good prize and 2 nothing prizes that don't matter. But the 1 good prize was always a big vacation, a car. I mean, it was worth a lot. And the other 2 prizes were worth nothing. So he says, I'm going to show you that that it's not behind here. You chose that. Would you like to switch before I make my before I disclose?
And then I say no.
And then the contestant would either switch or not. And the interesting property here is should the contestant switch? And in this case, the contestant chose the wrong one, and yes, he should have switched. Now it seems like a 50-50 proposition whether you should switch or not, right? Mm-hmm. But let's see. We're going to do this a couple different ways, and the first way we're going to do it is just to try it physically. We'll do this 10 times. I'm actually going to use a computer to randomly tell me where to put the ball is, so I don't add any personal biases in trying to be a random number generator, because humans are poor random number generators. So I will use a machine random number generator to tell me where to put the ball. Okay, go back to your soundproof booth.
Soundproof booth.
Yeah, and I'm going to do the first one. The computer tells me to put it here. Okay, come back. Okay, this is your first try. Here are 3 doors. There's 1 good prize and 2 bad prizes. What do you choose, sir?
I choose this door.
That's fine. Before I reveal the answer, I will show you that this one here has nothing. So now I'm going to let you choose. Just change I'm going to let you switch if you want. You can have the one you chose, or you can switch. What do you do?
I will not switch.
You will not switch. So we have no switch, and he's right. Big celebration. He wins with no switch. So that's a winner on a no switch. Okay, please go back, and I will use my computer to tell me to put it Okay, come back. This is the second try. And now choose again. Choose quickly, sir.
This one.
He chooses this one. Therefore, I will show you that this one is empty. You can stay or you can switch.
I'll switch.
He switches, and it's a winner. He has a winner for the switch on the... There we go. This is our 3rd time. Choose one. Choose that. I will show you that there is nothing here. And now, do you stay or do you switch?
I'll switch.
He switches, and here it is. And nothing. He switches and loses. This is try number 4. And what do you choose, sir?
First one.
First one. I will show you that. Here, we have nothing. Now, do you stay or do you switch?
I will switch.
He switches to this one. Dun, 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 dun. He loses on the switch there. Now we have number 5. And what do you choose?
The first one.
First one. I will show you that this one has nothing. And now you may stay or switch.
It seems like it's 50-50.
It does, doesn't it?
I'll stay.
He will stay, and he loses because here it is.
Ah!
That's a loss. Number 7. What do you choose, sir?
I choose the middle one, sir.
The middle one. I will show you that this is empty. And you may now stay or switch.
I switch.
He switches for a win. Number 8. We're going to go to number 10. So 8. Which do you choose?
I choose the first one.
This one is empty. And now, do you stay or do you switch?
I stay.
He stays. And there it is, ladies and gentlemen.
Nah.
A loser. This is number 9. Please choose one. This is an art. You are a professional now.
I choose donk.
You choose the middle one.
Yeah.
I will show you that this is no longer in the picture. You may stay or you may switch.
I switch.
He switches for a win. This is our final number 10. Please choose one.
1.
Fine, you've chosen number 1. I will show you there's nothing here this time. You may stay or you may switch. What do you choose?
I will switch.
He will switch for the win.
Yes.
That means
Silence.
switching. So here's our final tally. And we have, when you switch, you have 7 wins and 2 losses. When you don't switch, you have 2 wins, 1 win,
Yeah.
and 2 losses.
Seems like you lose a bit more.
And what can
When?
we say? That's pretty close to the predicted value of, it's not 50-50, is it? It's more like 2 to 1, right? If you stay, you lose twice as often. And if you switch, you win twice as often. Let's see if we can see that another way. And I've got another way to show that. I've got 3 ways to show this. Okay. The first way is as follows. The first way is choose a door. Doesn't matter because we're not just an exercise. Actually, choose one of these just to make it easier. Fine. Okay. Great. Now, you've chosen this one. All right. Now, this is how to think of it. I will give you a choice between either this one or everything in these 2. You can have it all. Do you stick with that or do you switch?
You switch.
Why?
Because that has a higher chance.
You're twice as likely, given that you don't know anything else, right? Here's the thing. I'm Monty Hall. I'm adding information by turning over a dud. I know this is a dud, okay? I am showing you where now it's no longer even. I'm still giving you this choice. By saying you can switch, I'm still giving you the same choice, right? But I'm making it look more difficult. I'm making it look like 50-50. But in fact, it's 66-33, right? 66% to 33%, right? And that's one way to look at it. Now, we're going to look a second time. This is going to be interesting. I'm going to put 100 doors down. So let's imagine this time, I'm going to show you a different way, okay, to understand this. Because this is hard, and people do get confused by this, and for good reason. This is a hard problem. People argued about it a lot when it came out. That was in about 1975 or so. But then it's pretty obvious. I'm going to show you another way to think of it, okay? Where's my ball here?
I think you put it in. Yeah.
Right, okay. Good. All right. Now, this is another way to think of it. Imagine there's 100 doors, all right? Choose one.
This one.
Fine. What are your chances that it's behind door number 3?
1 out of 100.
Yeah, 1 out of 100, right? 1 to 99 is the odds, right? So very likely this has nothing, right? But now I'm Monty Hall, and I'm going to say, fine, you know what? Let me just show you where it isn't.
Yeah.
Okay? I'm just going to show you. And now, what do you think? What do you think? You think you might want to stick with your original, or you think you should switch?
I think I would switch.
I'm giving you tremendous amounts of information now, right? Now it's 99 to 1 that it is here, right? It should be obvious that when you do it this way, you should switch every single time, right? And when you take it down from 99 to 100 to 99 to 98 to 97 to 96, and you go all the way down to 3 again, it's the same math. It's the same math. It's really 2 to 1. And finally, we're going to do it one final way, and that is to write a computer simulation, which I have here. All right, here we've built a simulator in Excel, and it's pretty simple to walk through this. We have randomly placed the prize, so I'm using a random number generator to get a 1, 2, or a 3 on this column. Then I'm choosing a door randomly, 1, 2, 3. Then Monty is going to show a seemingly random reveal, but we know it's not. So if it's under 3 and you've chosen 1, then he's going to show you 2. If it's under 2 and you've chosen 3, then he's going to show you 1. So this is calculated to show one that isn't a prize. And then this is the door that you have not chosen to switch to. And here we can see the win and lose percentage. When you don't switch, you see lose, lose, win, 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 lose, 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 win. You can see visually that there's more loses than wins here. And you can see here easily that there's quite a few more wins than loses. And if we translate that into data and make it into numbers, we could just zoom into this column and see that when you don't switch, you've got more zeros. And when you do switch, you've got more ones. And to quantify that, I've run this 100 times. And down here at the bottom, we've added it up, and we've got 0.32. And what are we expecting? We're expecting 0.333 and 0.666. So you can see that we're close after 100 tries. And I will throw the dice again here. So that's a new set. And let's just see how it came out after 100. And it's 0.32 and 0.68. So again, it's converging toward 0.33 and 0.66. This is the third time I'm trying. And look at the variance here. Look at that. I've got 0.41 and 0.59. That is the variance because it's only 100. But if I used 1,000, it would be much closer to 33. And this is the fourth time, 0.35 and 0.65. So what have we learned about this tricky little situation here?
Your brain decepts you.
Yeah, if I expose 1, it looks like a 50-50 choice, right? You think, well, now I can't be any better off. It's just a 50-50 choice. But that's not true. You're actually twice as likely to win by switching, right? And do Monty Hall problems come up in other situations in life?
Don't know.
They do.
They do.
Yeah, people talk about the Monty Hall problem whenever we look at in many times when we look at other problems, and it's a really good tool to have in your toolkit to spot it when you see that a choice between two things is not always 50-50.
Don't let your brain break you.
That's David and Shai for Cutting Through the Noise. See you next time.